Okay, hello everyone. We are continuing our season of design reviews for version 13.1 of Wolfram Language, and we are looking at, well, it isn't really discrete computation, but it's graphics and geometry and so on. And I think we'd gotten through effects and shading, and we're now on to filling. Correct?
Right.
I don't know whether, I wouldn't de-experimentalize pattern filling yet. I think it's fine, but I don't know how much it's been used yet. I haven't used it yet, ever. I kind of forgot it existed. There's some things I might have used it for, but I haven't used it yet. Do we know of uses? Okay, then then let's not de-experimentalize it. Okay.
Well, the proposal was that we haven't heard any complaint, but yes.
No, that's not a good answer. Let's leave it experimental. Okay. I think it's a slightly complicated story here that is, has yet to mature. I'll be more convinced if I've used it 3 times, but I haven't yet. Even though I really had forgot it existed, and I could have probably used it for some things. Okay, let's move on. If there's no region reconstruction mesh. Okay, so this is what we discussed some previous time in terms of naming. So this is given a bunch of points. This is produce a mesh that somehow interpolates those points, correct? That is not just a, like a specifically a concave hull mesh, but it's something more elaborate. Is that right?
Yes.
So for example, if I were to take, okay, so there's a random points, and that's reconstructing the annulus for the random points. That's nice. It's really quite nice. Yeah, great. Okay. Any more to say about this function? Hey, wake up, guys, this morning. Come on.
No. I mean, this is intended to be the top level, the most automated thing, right?
Yeah.
And it recognizes different dimension meshes.
Mm-hmm.
So you can recognize a curve, reconstruct a curve, or a surface, or a volume.
I understand.
Okay.
Right. It's nice. It's really a nice thing. It seems like a good, we can obviously try, basically and by the way, it should definitely point to random point, I would think, which is sort of the inverse of reconstruction mesh.
Yes.
And random point should point to it.
Yes.
And just for my amusement, if I were to make a random real, 10, 102 or something, and I would just to say reconstruction mesh of this, it should reconstruct a basically a rectangle.
Yeah.
Nice. It's really nice. And then if I wanted to, I could say something. How would I get the boundary of this? Boundary mesh.
Right? No, region bounds.
No. I want the actual boundary points here.
Oh.
I want
yes.
the thin. I see. Okay. Okay, cool. So I could then say something like, nice. Okay.
Yeah, you could do that for either one of them.
Yeah, sure. It's an approximation to 100.
Yes.
Okay, great stuff. All right, gradient fitting mesh. Okay, this is a more specialized mesh type, right?
Yes.
Which could be used by reconstruction mesh, yes or no?
Yes.
Yes.
This is the Poisson method.
Why on earth does it not point to reconstruction mesh here?
We will update it. We are still finishing the documentation, doing the deep linking and such. So it's still in process.
Okay, all right, okay, fine. All right. So I don't understand. At the normals at those points, how does it know what the normals? I don't understand. Gives it This gradient fits the best. I don't understand. How does it know the normals at these points?
So you give the normal. If you don't give the normal, there is actually a new function where we actually estimate the normal by computing the k-nearest neighbor. I think that's one of the automation actually which is added to those functions.
Okay, but I understand. But this thing here, P1, P2, P3, those are points of this form. Is that correct?
Yes.
So, I mean, you should make it clearer here that those are not just coordinates, which is what I would have assumed.
They work with coordinate. We take coordinate and we take also point. I mean, there is that whole stuff in geometry that we avoid, explicitly forcing people to use point wrapper.
I see. Okay, fine. But if you just give the points, then you have to estimate the normals using your technique. Is that correct?
Yes.
But you don't say that here. You don't say that here. Or estimated, I see. Okay, fine. Fine. Yes, you do. Okay, cool. So, and this is, I mean, if I did this in 2D, for example, what would it do?
This one doesn't yet work in 2D. It will, but it's not.
Okay, all right. So, I mean, if I gave it this thing, if I said, splash. Oh, I see. It doesn't work in 2D. So if I have to give it like points in 3D. That's rather nice. It's kind of a cool way of getting a random. I mean, I don't know what other ways are there of getting some kind of randomoid surface like this. It's kind of interesting. At least a neat example or something. Do you understand what this just did?
Yeah, you're doing a bunch of interior point, but this one doesn't. This one.
So I mean, instead of random point, in this case, we are pretty much trying to estimate the surface and hoping that we close, right? So.
Yeah. But I understand, but you're estimating the surface normals by you're effectively getting some local continuity of the surface because you're estimating surface normals from neighboring points.
Yes.
And so there's presumably a coherence length that I can define somewhere.
Yes, in some, not directly on this function, but yes.
Okay. What's new here?
The dimensions.
So earlier, this function was returning d-1 dimension based on the embedding dimension. Now you can ask, the specific cells dimension. So maybe you want 0, 1, or 3D.
So in other words, you're saying if I want just I want a bunch of planar facets interpolating through this thing here, right?
Yes.
So I mean, rather than if I just say concave hull mesh, what's the alpha parameter? That's some kind of
That's the radius of the bulb. It's kind of a closeness.
What does that mean? Why did it do that? Okay, there we go. So that is a d-1 dimensional. So that's a surface fitted through those points, correct?
Right.
But if I now were to say comma 1 here, I would get, oh, that's very cool. Lovely. These are nice. Okay, where am I storing this stuff? Where am I storing this? Anybody know?
Put it in graphs, please.
Okay. Okay. Estimated point normals. Okay, that's the function you were just talking about.
Yes.
I see. So it's just going to return a bunch of normal vectors for these points.
Yes.
vertices of that mesh. So what does it do when it, okay, so I don't quite understand how I make use of this thing. So if I say estimated point normals, God, I hate the way that you do this with PTS equals and then PTS inhibitor, whatever. And that's okay. It's all right. It's not as bad as it might be. Okay, yeah, because this is what I was wondering about, is how do you make use of, so I mean, in most uses of this, you're going to want to thread this into the thing that you're dealing with, right? Am I making sense? You're going to need to
to attach the normal to the point.
Yes.
But there are other uses, Stephen. You might have a graphics complex, that you want to add, surface normals to smooth it.
I understand. But in all of these cases, what you're basically doing is sprinkling surface normals into a structure that already exists. Correct? In other words, what you really want is not, it's more like, I mean, I don't think this is necessarily the right.
Well, I think that this is a low-level function. I think that we provided sort of low-level programmer interfaces too. You don't need it. We automatically do it for you.
I see. Okay.
In these other cases.
No, but I'm just, hear me out for just 1 second. I mean, the main issue is you want to insert into existing data structures the normals. Okay. So what I'm wondering is the right function a thing that contains a function, or at least can optionally contain a function that instead of returning the normals here, it returns effectively the normals, knitted according to some function. Did you understand what I'm saying?
Yeah, but we have to enumerate, so that won't be complete, but we can enumerate some of the use cases. So you just mentioned one, which is point. There could be another one, which is polygon. There can be another one that's polyhedron. There can be another one that's mesh region.
I understand that. So what I'm suggesting is,
but I don't think that those even enumerate all the cases, because when we provide low-level programming primitives, which are viewed as being, then we don't, that's the point of it. We don't anticipate all use cases.
No, I understand, Roger. I'm just trying to say that in a case like this, right, what you actually want is to inject vertex normal options into those points, right?
Yes.
And estimated point normals.
And the right way to do this point is to use multi-point, and then you have a list of normals. So it's not a hard thing to do.
I see. Okay.
Unless you use this.
Fair point. Okay.
And the same apply also for mesh. That's why you see we're adding the second argument there, where you can give the mesh and then we return you the normal based on your ordering of your vertex coordinates. So you just map it directly.
So how do you put? Okay, so the point is that, so in this case here, I mean, I understand the point of this function. I'm just saying, okay, hold on. Let's take this as an example. Okay, there's the multi-point thing, et cetera. And now it's just going to return for me the, just the list of normals. But I don't quite understand, maybe it's a different function, but maybe it's not useful. I don't know, insert estimated point normals, basically. That is, take the data structure that you have and spray that in. That's an operation we have not done very often. I mean, we could imagine, for example, for a graph, it's something where we normally don't do that. Like, it's not the case that, let's say the chromatic number of a graph, or okay, for graphs, what we're doing is similar to what you're doing here. That is, okay, you know the list of vertices, vertex list, and if you want to know the, vertex out degree or something, vertex out degree of the graph just gives you that list in the order of the vertex list, if I'm making sense.
Sure.
Right? And this is the same type of thing.
Yes.
Right? And so I'm kind of unmaking my own argument to some extent. That this is like vertex out degree applied to a graph. This is estimated point normals applied to a mesh, just returns in the order of the mesh points, which you can extract from a property from the mesh.
Yes.
It returns these things.
Yes.
Okay. Okay. I'm not objecting. Okay. Sander is asking, for 3D, does it give normals versus points, edges, or faces for points, edges, and faces?
So the method we are using is a plane fitted, like rated there. We are using the hyperplane. So if it's in 3D, we are going to use pretty much try to pick point or estimate the plane on that. So the D-1 dimension.
But he has a point. But I mean, we could consider that. So if you have, let's say, a polyhedron or a mesh, you could attach a normal to an edge. I mean, so to the corner point, which this one does, or you could attach a normal to an edge or to a face, all of which is possible.
Well, you can attach information. I mean, it depends on how you interpret it, right?
I didn't mean attach as in attach within annotation. I mean that you can compute it. There's a well-defined normal for an edge. There's a well-defined normal for a face, and so on.
You start to get into the gray area, even in this case, right? Because then you get into the weighted normals, and then there is a different way to weight the normal, how you apply it. So that's why we are trying to extend it later on with several methods, and then we can cover any way people want to compute normals, right?
Okay, but why didn't this work?
Oh, we are still implementing it, so it's an extension. Yeah.
Okay, but it will work.
Yes. So if you do, I think if you do mesh coordinate around that, it may probably work.
This thing, mesh coordinates?
Yes.
And I assume these are unit normal vectors. Is that correct?
Yes, they should be.
Okay. So I mean, if I were to do this as a, I don't even know how to. Wait a minute. Oh, I see. That's at the points of the polyhedron. So I would have to transpose this in to make the hedgehog, so to speak, to make the outgoing arrows, right? Okay, let's come back to Sander's point, which is right now we have got for a given mesh, we are only taking its points as the places for which to generate normals. Right, but I think Sander's point is that you could perfectly well, like for this dodecahedron, why are we taking I see, because it's called estimated point normals.
Yes.
Right. You could have it equally well have a thing estimated face normals if you knew what the faces were.
Yes.
Okay.
I mean, you don't even need to estimate them.
Well, in the case of a dodecahedron, you know what they are. Yes.
Right. I mean, if it's a mesh polyhedron, there's like no estimation. It is what it is.
But what I pointed out is that they are not actually unique on the face too, right?
What? I mean, there are two of them, you mean?
Well, the normal on the face, you're assuming on the distance, right? The same as we do on graphics. You can, build the normal based on the weight of the vertices. There's several versions, kind of what I mean. So it's not just one standard way to compute the normal for a face.
I don't know. To me, the face pretty much has one normal. There's no.
Okay.
It's a planar face. It has one normal.
One normal. Okay.
I mean, but I don't know what use case you're thinking of, but it's kind of if you want to round them out or something.
Well, wait a second. I mean, there's also crazy faces like ones where the thing is not, is specified in some kind of weird bow tie type thing, and it's not planar, given the points.
But those are not really faces. That's like, yeah, that's.
I'm talking about the case like the Guru shading, right? The face normal estimated
I get
from
it.
the vertex.
Oh yeah.
I mean.
I get it. Yes.
What are you saying there?
Well, there we get corner normals, vertex normals, and for Guru shading, we then compute colors in the corners, and then those are interpolated across.
I see. Craig on the live stream is saying this is going to be very useful. Then it's also saying it'd be nice to be able to interpolate normals at any point on a mesh. That is what you're doing here, is you're delivering, given the points, you're delivering what the normal is estimated at that point. But I think what Craig
Actually,
is
it's
asking,
not a bad idea.
right? So in other words, it's a function. It's
how would one specify
well, you basically are
a
giving.
point on the mesh?
Well, it's like okay. So here, look, it's like interpolation, right? I mean, you're basically.
Oh no, you have to kind of do a closest point or something, because there's no coordinate system on the mesh.
Why isn't there I don't understand that. I don't understand. What you? Oh, I see what you're saying. You're saying you don't know. These are points which are guaranteed to be on the mesh.
Well,
Sorry,
they're
not these
attached to
points.
the corners. Yeah.
Yeah. These points here are guaranteed to be on the mesh, right? So if I do, for example, here I say reconstruction mesh of this. What's it going to do? Oh dear, that does not look much like a dodecahedron to me.
Well, you use the
So currently the method is kind of right, especially, I mean, the method we currently have, we are trying to assume that the surface you want to rebuild is smooth, right, and such, and close. So.
Okay, so we lost some, what happened here? By the way, you should put this in a possible issues thing in reconstruction mesh. Okay, what happened here to my dodecahedron? I got one nice pentagon there, but what else happened?
Well, we try to reconstruct it from the object. So unfortunately, there's no full guarantee that we'll recover everything.
If you just sprinkle,
so we need more data, right? So
if you get more points, the robustness goes up. So
okay,
you can do random points. Let's say that the boundary region for dodecahedron. Do sample the boundary, not the interior, so you get the surface.
So how do I do that? Boundary. What?
Region boundary, right? Or boundary region, yeah, region boundary, dodecahedron, and now sample. Yeah.
And now I say reconstruction mesh of this.
It will still look smooth, probably, but less.
What's going on here? Why does it surprise you it's taking so long? That's pretty good. Nice. Okay, so now what I'm saying is, let's see. What you're saying is, if I state just a random, I mean, okay, so here's what you could imagine. You could imagine a normal field, so to speak. That is a field, a vector field at every point, even in space. There's an interpolating vector field of what the normal direction would be if the mesh, were to go through that point in space.
Yes.
I mean, that's a sense. But then the question of whether, how you get to the point that's actually on the mesh that is near the point that you're specifying is not so obvious. You might drop towards, I don't know what you want to do, go towards the centroid or something.
Or you could do the nearest point, for instance, if you want to do that.
Yeah, I see. The nearest point on the, region nearest.
Yeah.
Yes. Well, it does seem like an interesting, it's a good WFR function to start off with, to find the interpolated, given a mesh and given a point, what is the interpolated normal, for that point that isn't one of the actual points on the mesh. Does that make sense? Yes, that's what we're talking about, right?
Yeah.
I mean, it'd be interesting to know what some use cases are, whether that's a thing that we should be thinking about as an extension to this estimated point normals thing.
Well, it would be interesting to hear from that user what uses
he or she had in. All right, let's move on. But that's interesting and at least a good WFR possibility. Okay, mesh region. Supported polyhedron cells. What do you mean by that?
So we had special for 3D. We supported things like simplex and hexahedron. And so there are about 4 special cells that can be supported in 3D. Now it works for any polyhedral cells.
So you mean I can extract dodecahedra out of some random collection of points?
No. A mesh region is built up with cells.
Yeah. Okay.
See what I'm saying? So you have to specify all the cells. So like in 2D, you can have any polygon as a cell.
I see.
Do you understand?
Yeah.
No, this is the analog in 3D, that we can have any polyhedron as a cell.
But they may not tessellate space.
Well, then it's, well, no, but yes, but then you have a weird mesh region. Yes.
Okay, fine.
Mesh region
So-
allows for that flexibility.
But so simplexes, you're saying you're generalizing from a simplex to an arbitrary number of faces on the polyhedron.
Yes.
Okay, fair enough.
So you have honeycombs and other things, you know, and Voronoi mesh is an example of that. You know,
Okay, are you telling me that we finally have 3D
yes,
Voronoi?
yes.
Oh my gosh. How do you realize people have been asking for that for 20 years and we have to apologize every time that we don't have it? Okay, show me a 3D Voronoi. This is exciting. Hold on a second. I got to do this myself. Okay, so random point, let's say 10, 30, 3.
You want random real?
That's what I want. Yes, thank you. Okay, and now I say Voronoi mesh. Da-da-da-da. Oh my gosh. Look at that. And now, so can I, if I show this with, can I show this with opacity?
Yes, you do mesh or you add the option of mesh region.
Well, why can't I do region plot with some opacity?
No.
Well, you can do it, but I cannot guarantee that it will work correctly.
No.
Why wouldn't this work?
No.
We still have to work on region plot and extend it. It won't work.
Well, it's a 2D plotting function to begin with, but you know, but even that, it's not.
Right. I mean, the purpose of region plot at the time was not.
Okay, I think this should work.
I mean, that's the correct region. You just saw it. It just doesn't show your partition, which you probably want to see.
I see. Okay.
So if you do a mesh region and then
you could do it directly in the Voronoi mesh too.
Okay. All right. Okay. Go ahead. What do I want to say here?
For example, base style goes to opacity.
Magnificent. Boy, people have been waiting a long time for this. Why was it so hard?
Because,
I mean, it was.
Oh, go ahead.
Well, it was
Better
not
have been
hard.
hard because people have been asking for this for 20 years.
I mean, the key thing is that we needed that support of polyhedron cell in mesh region. That's the key thing. So we need to be able to compute on it besides just looking at them, right? Looking at the Voronoi.
Okay, so for example, let's say I want to take this thing and I want to shatter it, and I just want to have all those separate polyhedra, all those polyhedra.
Mesh cells.
Okay.
Or you use mesh
Which
primitive.
dimension? You know, you probably want the
Dimensional cells.
yeah, that come with yeah.
Okay, now how do I visualize those?
Well, you
Use mesh primitive.
yeah, use mesh primitives because then you get the coordinates stuck in there directly.
How do I do that?
Mesh primitives instead of mesh cells. Actually, no. Here's what he should do, Charles. He should just get mesh coordinates, comma, mesh primitives. Sorry, mesh cells. That's the efficient way to do it.
This thing here.
No, so do graphics complex.
You can do graphic complex, mesh coordinate, comma, mesh cell.
Yes. That's the efficient way to do it. If you want to look at no, actually, that will just show them again. That's no point. That's not what you want.
I want to see the things. Look, I've got.
No, I'm backing off. Let's do mesh primitives and just wrap graphics around it, or
Mesh primitives, comma 3.
Yeah.
Map graphics around the map graphics onto the whole thing. Graphics 3D.
Yeah, graphics 3D. There they are.
Okay, nice. By the way, you should use that as an example. I mean, not maybe one with this many, but that's really cool. Okay.
And whatever you want to compute on those primitives, like the areas or, volumes and centroids and other things.
Right. So what I could do here is I could say something like volume slash at mesh primitives of that. Yeah. And then I could say histogram of those volumes, and I could see how well it managed to get them to be equal volume.
Yeah.
this is exciting. This is so long, you know, yeah. It's just like I learned been writing this history of the NKS book, and whenever you see in a book description this long-awaited work from so and so, it means the author was 10 years late in delivering the book. So this is the long-awaited function, 3D in Voronoi. Never mind. It's really great. We have this. Okay. All right. Onward. Integrate. Okay. Go ahead.
Well, it's not in the prototype build right now, but it's has, you know, the example is there. We are extending it and making it more, improving the performance and the robustness.
So what was not? I was surprised that didn't work previously. This thing here.
Well, it did work, but it was not using. I mean, we haven't really fully derived the closed form formula. So
I see. So n-integrate would work. The syntax would work, but the formula would not have worked.
Right.
So we've derived, we've derived and very efficient sort of polynomial integrators over all special regions.
Okay.
Okay.
What kinds of functions do they involve?
Well, it varies. This one turns out to be what?
PF1.
2F1, yeah.
Okay, so they're typically hypergeometric family type things.
Well, some of them are polynomial. If you integrate the simplex, polynomials over simplex, it's polynomial.
Okay.
Yeah,
but I mean, you've got these are quadratic
gammas.
Right, but these are fundamentally regions defined by quadratic constraints, are they not?
Yeah, this one gets 4th order though.
Okay, but I mean, given that the constraints are quadratic, what does that tell you about what functions will be involved in representing the integral?
I think torus is not quadratic; it's cubic.
Oh, is it?
Yeah.
Okay. Well, it's cool.
But cylinder and ball and so on are quadratic, obviously.
Mm-hmm. Okay. Regions with parameters, non-constant regions. What does that mean? Oh, you mean that I can put a parameter into this torus? I can say a torus. I
think this means generally we've improved our capability of integrating and dealing with parameters in regions. Yes, we can. We've always been able to have parameters in regions, but it's probably been improved.
Right. Okay. More the symbolic side of it.
Okay. Infinite line through. So we've had line through for a while, correct?
No, we have infinite line, and these are coming from the Michael team, synthetic geometry, where they wanted to describe.
They're used in the opposite way. They're used to provide constraints, because if you have more than 2 points, there's no guarantee that they are in a line at all.
Yeah.
So they they're used in the opposite way. They say these are on a line.
Okay, but so what does it do? Yeah, no, I understand. But what happens if I give non-collinear points?
It returns unevaluated.
Unevaluated.
Okay. Do we have somebody from that team here?
No.
Okay, so I want to look at this with those guys.
Okay.
Can we either find somebody from that team? Because I don't really understand this. I mean, when we say circle through, for example, if I say, for example, if I give it a bunch of points, right, and I say something like, I mean, again, if we can find somebody from that team, that'd be great right now. If I say this, right, and I say circle through.
You have to be in 2D first.
Thank you. Oops.
Who would you like from that team to join?
I don't know. You have to ping Michael and ask him who's relevant. Okay, so if I now do this with 4 points, it's going to say no luck.
Well, it's depend, right? So we use the first 3 points, and if we manage to check that the 4th point is on the curve, then we return it.
I understand. But so let's look at the documentation for circle through. Huh. Okay. So you're doing something directly analogous to that.
Yes.
Let's get somebody from that team. Let's ask about this for a minute, okay? Because I don't fully understand how this is used. And I don't see why this one doesn't have examples of that.
Well, I got equally confused as you did, just as you did now, Stephen, until I realized that that's the use case, is to provide a constraint to say
Okay,
that
let's get somebody from that team and let's hear about how that works.
And so I think they were incorrectly documented, actually.
Sorry, I disagree. I mean, there is two things, right? Synthetic geometry want a representation, and then there is the analytic part, right? So this function covers both.
Okay, let's get somebody from that team and let's discuss it when they're here. Okay, let's keep going. Geodesic.
No, I started thinking about, it's like, does it use least squares? Does it fit? No,
right.
It doesn't do that.
Guys, stop. Let's get somebody from that team. Okay. Okay. Geodesic polyhedron. Okay, we just talked about this yesterday a bit. So I don't understand if I can say geodesic polyhedron, what's the difference between this and a communal garden buckyball? Is that in fact a buckyball?
No, the buckyball generate hexahedron, the faces. This one are more triangles. And it's more a kind of a subdivision on approximation of a sphere or a disk, if you want. So,
okay, so I don't understand. So this is when I say 3 here, this is a decomposition n times. You're subdividing n times here. Is that correct? Let's be very basic. Splaffaroo, why doesn't that work? What should that do? You're subdividing here. What is the base case, the 0 case?
That 1 is the base case. We never index stuff with starting with 0 in principle.
No, I understand that, but what would be, Sandra's asking, is this convex hull mesh of sphere points of n? No, it's not, right? Because sphere points is yet a different thing, although that's a very good example of, sphere points will attempt to equally space points on a sphere. And so that will produce for you a much less regular looking object, he says. What the heck?
Michael Trott is here.
Hello, I just joined.
Hello. What the heck is this?
That's the most symmetric object you can make with 20 points.
Oh, yeah, so it is. Right. Let's do 25 points. That's more interesting. Oh, lovely. We could have made those 25th anniversary spikies right from this, probably. That's cool. Okay, so this is 100-faced. Okay, so it's interesting to compare that with this. And by the way, this should be both an example in sphere points and an example, I think, in convex hull mesh. Good idea. But in this case, I'm just trying to understand the subdivision number here means what? One subdivision. Is this one subdivision? Charles? Roger?
No, this is the original. In this case, is the icosahedron, I guess.
Okay, so that is the base case of the generic geodesic polyhedron.
Right.
And so if I go to 2, I will take every face of this and subdivide. Is that correct?
Yes.
Okay. Okay, the question that we had for Michael has to do with infinite line through.
Yep.
Okay. And we want to understand what, explain the use case in geometric scene.
Basically, a line in our world can go back, forth, left, right. We want something that is a line in the classical sense with points ordered along it.
Oh, boy.
Okay. But Michael, my understanding is that you use it to constrain it. If I give you 3 points, with probability 1, they're not going to be on a line, but you
That's correct.
support the, 3 or any number of points. So it doesn't even make any sense in general, unless you say that you approximate them to a line. But you mean that?
But you have a collinear, you have something that says collinear. What is collinear points? Collinear points is the condition, whether the points are collinear, right?
Yeah.
Okay, so now what is infinite line through relative to collinear points?
That's a line. The other ones are points.
That's the actual line, the constructor, right?
Collinear point, as the name says, is a set of points, not a line.
Yes. But okay, so look.
But then it makes no sense to support arbitrarily many points. They're never going to be on a line.
No, but
what do you mean by this? Like you state that they are on a line.
That's what I was just telling you. You use it as a constraint.
Well, or alternatively, okay, so look, infinite line through ABC, basically, where these are, so if I do this, if I say something like geometric scene of AB, if I could spell, of ABC, right?
That doesn't work right now, but yes, this is exactly the case.
Yeah.
Okay, and then I say random instance of this.
Exactly.
Right. Then the only thing we were using different vocabulary to describe the same thing.
Right, but the main point is this is then a symbolic. The most interesting use case of this is a symbolic use case, not
Yes.
a concrete use case, which is
Correct.
not what's documented here at all, and it's just totally confused.
no, it's not confused. We are writing the example. It's written in the details. We are not confused. It's written in the detail. We are updating the documentation. We are waiting on examples. It's not the final version in terms of examples.
Okay, but
The only
Why
key
didn't this
thing is that on the usage, we could have said infinite line 2 represent an infinite line. We choose to say give an infinite line. So it's a
which
matter
is
of
wrong.
choice.
Yeah, right. Which is not it is making Roger and me at least very confused.
But the next line, we adjusted it. We say it's typically used to specify the
Okay,
constraint.
but I think you should reword the thing at the top to make it clearer. Okay, this
Sure.
says represents a circle, which is much clearer. Right, that's what you should do here. Represents an infinite line going through these points. Now, Michael, why didn't this work?
Because this one.
This one here with circle through.
This is a good question.
Okay.
This should work. I'm not sure right now.
But then what that should do is I should be able to ask the question, given that there's a circle through A, B, and C, what is the angle between, what is the angle ABC or something? Right? How would I ask that question? Assume there's a circle through A, B, and C. What is the angle? The angle at B.
Once you get your points out, you can do that, right?
Yes. I don't think you can ask this in one get-go.
Okay. Okay, but that's a reasoning thing that one should potentially be able to ask symbolically, is if I assert that there is a circle through A, B, and C, then I should be able to say, what is the function that gives me an angle?
Planar angle.
Okay, so
this is very much not unique at all. Like there are infinitely many triples of points on circles.
Yes, right, with different angles, right?
Yes.
Although, right, but anyway, okay, I understand. So I think there's a little bit of redocumentation needed here. An arc through is, what is the difference between arc through and circle through?
It's not a full circle. It's a circular arc. Maybe it should be called circular arc, actually, because it's not a general arc. It's a circular arc, right?
Yeah, I think so. Do we have the notion of a circular arc? We don't have a circular arc primitive.
No, circle has it built in.
I know that.
Since 30 years ago.
Yeah, right. Although, how do you specify the arc? In the case of arc through here, how are you specifying the arc? Is it specified using a circle specification, or what's the?
No, so this auto-evaluation, so this is actually useful. The auto-evaluation, when applicable, it converts it to a circle primitive.
Right.
That is useful.
Right. And so we have more of these things, circumcircle and so on. Do that. They basically auto-evaluate.
I think the circle through you just tried that didn't work. The second argument has to be a list, not the raw primitive. It works just fine.
Okay, that's just a minor baguette. I mean, it probably shouldn't need to be a. Lovely. I mean, you should fix the baguette. Of
Okay.
That
Okay. Yeah.
That's lovely. Okay.
Nicely spaced.
We put a reasonable amount of effort over the last weeks and months of this.
Okay.
It's still some things to be done, but good, much better.
Why do you have to have a thumb here rather than this being the overall? Why is this not the overall outer? What's it?
There was something. I don't remember right now what was the reason.
This is pretty fancy. I haven't seen this before. Wow.
Oh, I'm pretty sure you did. We had a couple of meetings about it.
That's lovely. Yeah, okay. All right, so this, what do you think? Circular arc through? I think it probably should say circular arc through. Agreed? Yes? No?
I think that's the better name. We have a bunch of other arcs.
Yeah.
Even though they.
Any objection to changing this to circular arc through?
Should it be then segment? Circle segment?
Why isn't it called circular arc? Isn't that what it's called? And that's what it says here, isn't it? I mean, that's what it calls itself. Right? I mean, it says circular arc. So unless that is wrong, this thing should call itself circular arc through.
No, sure. I mean, it's fine.
Okay, fine. No objection. All right, so let's move on. Okay, I think that's what we needed Michael for.
Okay, then I go back to my other meeting.
Thanks a lot.
Thank you. Bye.
Yeah, bye. Spatial point data. Oh, that was the bug that I had found, yes?
Yeah, I think so. That was one of the workflow things.
Now supported by all geometric functions. So what, explain, I was doing that elephant thing, right?
Mm-hmm.
What was so what did I have? I had a bunch of geo.
I can't remember what you did, but workflow thing should work, you know, that this is another collection of points that's common.
Okay, so for example, if I say something like, and then I say,
what? Well, this is not what we were talking about here, but what on earth is happening here?
It's a bug.
Well, the first line tell you, right? We probably mesh region just rejected because it's constructed a non-coplanar polygon. So.
Okay, I roll, but I mean, this should work, right? We agree this should work.
Well, yeah, spatial point data, I think it did accept entities, you know, and
it does. It seems to accept entities, but for some reason, Europe is not flat enough for it.
Oh. Could you just save this so we can, you know, calmly look through what the heck's going on there? Just like.
Yeah, I am saving it.
Okay. Wow. That's pretty spectacular.
And Kristen will give you the material from this. Okay. Well, there's nothing more to. But what does this mean here?
It means that you know, let's say that, you know, an awful lot of functions in geometry, they take a list of points, and now in place of that, you can use spatial point data. Nice, huh?
Oh, in place of the. Okay, so for example, if I were to give you, let's pick a spatial point data thing here.
Let's say that you generated a bunch of.
Yeah, I want to generate. Where do I have a bunch of spatial points?
We can generate them from all
really
kinds of.
should say n of, not n at sign there. I mean, just give people a chance. Okay, so here, if I say, well, let's do spatial point data of two-dimensional spatial point data here, and then I say Voronoi mesh of that. Ooh, why didn't that work?
That should work, I think. Charles?
Yeah, I don't need to double check why it. No idea why it's rejecting it now.
Okay,
It's something we need
fine.
to double check.
There's some bug.
Right.
Okay, all right, let's move on. But then treat it as points, so that the data in the spatial point data is treated as points.
Yes. Isn't
Right.
that amazing?
Yeah, well, right, the way it should be. I mean, so I mean, for example, I could as well say here 3, and then in principle, I can now say reconstruction mesh of this and so on.
Yes. Yes.
Okay, except it doesn't work right now for some reason, and the message is not found, and it's just generally
Well,
the
yeah.
animal is dying with some, flailing characteristics. Okay, all right, let's keep going. Wow, that's exciting. So if I say random graph of, let's say, 50, 100. Okay, now what can I do here?
So you add the option editable goes to true.
What happened here?
You can select the point like in graphics, double click, the same as the graphic. So you are moving the whole graph, or you can double click like in the graphic editor for current behavior.
Come on.
There you were changing the bounding box. You have, there is all the different state in the graphic editor, right?
Okay, guys, this needs a proper review. This is not sensible. Okay, how do I move that point?
You select the point and then you move it. You are picking the bound.
Okay, so there I've got the point. Come on.
Stephen, is your selection mode is exactly the behavior of a graphic when you edit
I understand,
graph.
which is the wrong thing. I mean, that's why I'm saying this needs a proper review. This is not right. You should not have that be this default selection mode, because you're going to get this kind of nonsense when this is not what you want. Right? Help me out. How do I select the point? Is that it? Oh yeah, finally I got the point. That's lovely. That's magnificent, Charles. But let's set it up so that's the default rather than, splitting out these things, which is what you want for graphics editing, but not for graph editing.
No, Stephen, Alice I can turn off that option, but when you select a point, you get the bounding box. So if you stretch the bounding box, you stretch the point.
Nobody's going to figure this out. Nobody's going to figure it out. I don't just switch it off. Let's have an actual review that involves UX people, and let's try and figure this out. I also don't agree that, for example, this border not being purple anymore to indicate a graph isn't right. See what I'm saying?
Sure.
Right. Let's get a meeting about this as soon as we can. Hopefully it will be straightforward to just switch on and off a few options, and then we'll have something wonderful. That makes sense?
Yep.
It's really great that this can be done. Really great. I mean, that's another thing that's been requested for a long time. And I certainly use it all the time. How big a graph can I realistically deal with? How big a graph?
Any graph size, as long as we can render it.
Okay, that is also wrong.
No, we are still working on the, making the expression back, the whole process. So
okay, fine, but please get a review. of this, okay? Hopefully in the next 2 or 3 days, right? So early next week. And make sure we include design and UX. Fair?
Okay.
Okay, so you think that this will work, basically? If I can manage to somehow miraculously, oh, for God's freaking sake, come on. Okay, so I've got that point now. Now, what do I do? What do I move? Do I move? Haha, it's a joke. Come on. Tell me how to do this. What am I trying to click to get to move a point here?
So you have a point. Let's take one outside. What?
No,
Click
no,
on
I
it.
want to take that one there. Okay, yep. Now, got a little white dot and I've got a purple dot.
Okay. Then you move it.
How do I move it? What do I click?
So you first have to select the point.
No. I've got a selection. What do I do now? I've got a selection. What do I
Steven,
move?
this selection state was defined by the graphic. That was not
I know,
even
which is
defined as
wrong,
state.
which is not what you want, because it's doing this kind of stupid stuff. Right. Anyway, we'll review this separately. Okay. Okay. Spatial graph distribution. That's what I was just looking at. What does this mean? What is, I don't
It
understand.
connects edge. If you have nodes and they're within a certain distance, there's an edge between them. So for instance, if they're like radio transmitters, if they're close enough, they can communicate.
What is the difference between this and nearest neighbor graph?
What's nearest neighbor graph?
This is a uniform sampling distribution when nearest graph is a constructor, is a fixed one. Right?
This one we defined early on for random graphs.
So in this case, this extension is that you can take a disk, for example, right? And uniformly, sample 100 points on that disk and then connect the one which are the closest,
Oh, nearest neighbor, the nearest neighbor in the graph
Yeah.
sense. Oh, no, I'm sorry. No, this is spatially. You spatially
Exactly.
puts point out.
No,
and-
but no, Roger, look. I have to go in a second here, but see this?
So here the points are fixed,
Okay.
right?
So what's
Where the spatial graph distribution, you sample, so you give the region, right? Let's suppose, it's a rectangle, like in the case of, random real 1, 2 is equivalent to essentially say spatial graph distribution, right? On a rectangle, on a square, 0, 1. Right? So you sample the point in that square.
So you're saying in this case here that I say, what is, I mean, I don't understand.
10.1.4, right? And then you put disk. And then you do random graph around it.
So if I make this like 100 or something.
There's a beautiful application example with frogs jumping on lily pads in the applications.
How does this relate to the sprinkling stuff that's been done on manifolds?
What? I have no idea. Well, this is from version 9.
No, but the fact that, well, okay, hold on. Let me look at this for a second.
I think this relate to the intrinsic curve manifold to graph, right, coming from the physics project. So this functionality actually covered that one, that intrinsic curve manifold, extrinsic curve manifold, I think. That one.
Does it?
Yep.
So, but now this is so okay. So again, we need to make these connections. I mean,
Well, this was done
I mean-
first, so
no,
causality,
but
causality,
Wait,
time
this
moves.
wasn't done
we-
first because we didn't have, or was it? I don't know. Maybe this just uses spatial graph distribution under the hood.
right. I mean,
I think it does.
we are planning to put an application and then make the link with this function repository if you want. But it's
Okay, fine. That seems useful. Okay. I mean, maybe this just uses spatial graph distribution underneath. I don't know. You can obviously determine that.
It's not the hardest function to write.
Fair enough. Well, anyway, it seems I understand. I was just trying to make my cognitive connection to understand what the heck this thing is.
Makes sense.
I
I know you have to go to source.
Yeah. Now, how does this do in terms of the calculus of annotations?
at this time we don't yet support the calculus of annotation. It's something we progressively propagate through the system. It's expensive, it takes time.
So this is based on the actual names of the vertices. This combines them. Is that correct?
Yes. Actually, based on the
Index,
vertex list, the order in the vertex list.
because the sum is based on the sum of matrices.
I see.
And
I don't know these definitions, but I mean, so that means that if I don't quite understand that. I mean, it's if I have A, B, and C, and one of these graphs lacks B, for example, I can't do this sparsely. I have to do it with the dense representation in terms of the sequence of indices.
Right, or pretty much we extend it is, essentially we work on the indices ordering. So it doesn't matter even if you have, A, B, C, and C, and then, 1, 2, 3, 4.
Well, yeah, graph union does the thing that I'm describing. Is that correct? If I have graphs, what's that?
Yes, graph union does it take into account the explicit vertex, right? If you see what I mean.
Right. But this name seems confusing to me. Because this is, go ahead.
Well, this is the standard name in the nomenclature where people define it: graph sum, graph union, graph disjoint union, graph product.
Okay, but graph union is doing something different. It's using the actual, vertex names of the graph, whereas this is using the vertex indices.
Yep.
Right?
Yes. So
is that
essentially,
part of the literature or not? Or is the literature blind to whether you're using names or indices?
it's pretty much blind. I mean, there is always that in general, what people actually manipulate it, on label graph, where, in the language, we're actually dealing with graph with labels, right? So, sometimes you have to reconcile both concepts.
Right. Listen, I really need to go. So let me just look here. We have another a catch-up design meeting at 5:30 Eastern today. Could we add in a few of these little loose ends to that, if possible?
Yeah.
Okay, that's an issue for. Okay, I need to
Corey.
run that.
For Corey.
Yes, and if we can get some UX folk there, we can talk about this graph. I
don't think we'll be able to get through all this in 30 minutes. Just don't think so.
Okay, well, fine.
And the calculus and algebra stuff too.
Then we'll have to reschedule for Monday.
Yeah.
Okay, this is really good. We're really close, but I really need to run.
Okay.